Hopefully you're going to enjoy this. I usually get pretty good feedback. It's a fun presentation. And what we're going to talk about is artificial intelligence. We'll go through some of the workings, history. I'll show you a demo or kind of a model. We'll walk through one. A little bit about my background. 21 years in the military. I started out in the Air Force playing around with nuclear weapons. And then I went over to the Army and flew helicopters for a while. Not an easy transition, but it was a fun one. Had a lot of different various leadership roles, threat officer. I ran large and small organizations and things like that, and I was actually a test pilot for a while. And I got out in '97, and since then I've been in the IT kind of field. I got into security in about 1998, so I've been at this for 20 years. Anyways, some of the places I've been. NASA, JPL, World Banks, Chicago Mercantile Exchange, Delta Airlines, Corning, et cetera. A lot of interesting places. I've seen just about every industry. Like at Corning, there was an advanced persistent threat issue that arose. The Chinese were coming in and trying to steal everything they had as far as intellectual property, and they had some intellectual property. Corning does pure research in ceramics and glass and things like that, and they've been doing that since the early 1900s. And they have a vault of little discoveries that they've come up with over the years. And they have, I think, 4 or 6 PhDs, and their only job is to chew through that big mound of stuff that they've found through this pure research effort and see if there's commercial viability for it or not. The example I use is this Gorilla Glass in phones and TVs and things like that was actually invented back in 1964. There just wasn't a market for it. Store windows, they didn't want them shattering into big shards and things. Automobile windshields, the same thing. And so finally, and plus we blew up our TVs, into bubbles, and we put phosphorus on the back of them and shot them with ion guns, and that was our television. And so they finally came up with a practical use for it, and here we are now. But they were in there trying to steal it, and so we had to go through and try to harden operational control technologies and manufacturing. Very, very difficult with down-level OSs. I think they were running MS-DOS 5 on some things. So I've been a consultant, a practice manager, I've been a director of security, and I've been a CISO. I've created security strategies and implemented them. I've created pieces of security programs and helped implement them, like risk management or threat and vulnerability management, the services piece that security does for the organization. Currently, I'm a strategist at Fortinet, and it's the coolest title I've ever had. I think it's the one they give you before they stick you out in the pasture. But anyways, my view is if you can take technology and leverage that technology to help your critical, scarce, good security resources, and you take that effort of those two things and align it to the business, you will be successful. That last part is very, very critical in my opinion. Places I go to, first thing they say is, we ain't got no money. And the first thing I say is, show me a strategy. Oh, we don't have one. If you don't have a security strategy in place of some sort, if you were the guy holding the purse strings, having Scrooge McDuck bags of money, and somebody didn't tell you how they were going to spend it, would you give it to them? Very, very critical piece of it is aligning to that business, having that strategy. That's what allows security programs to succeed, at least be a little more successful in getting resources and things. But I digress. Today we're going to talk about AI. There's one primary problem with it today, and that is that everybody's yammering about it. When I first got into this business back in the late 90s, we played BS bingo. Buzzword bingo, I guess is a nice way to say it, where we'd take these latest marketing terms and we create bingo cards and go to conferences like this. And some guy would be up in the front saying, well, in order to go ahead and strategize on that layer, you have to think outside the box, and he'd start coming up with all these like gizmo terms that mean nothing, right? And we're stamping these off as he's going, and eventually somebody would scream bingo, and 13 other people would groan and tear their cards up. And right now, we have these terms like deep analytics. We hear a lot about that. We hear about crowd culture, virtual and augmented reality, big, way big, way big data, holistic eco fill in the blank. And there's three others that have popped up that we're getting slammed with. And that's the artificial intelligence, machine learning, and deep learning. These are subsets of artificial intelligence, and they each mean something a little different, but they're all relational. People want to sell things. They will call deep analytics artificial intelligence, whereas it's just a big computer looking at big piles of data and coming up with some fairly big decisions. It's not necessarily artificial intelligence. What is it? Well, when we think of AI, we've got this little vision in our head that this electronic brain is taking care of us in some kind of a fashion. It's doing the right things, that airplanes are landing where they're supposed to, and all the traffic lights are working in our city the way they're supposed to, and things like that. And we also hear some scare stories about this. And one of the more interesting ones was about a year ago. Computer. There we go. Facebook, there was this clip that came out, said Facebook had this emergency shutdown. And you read the article, and it sounded like some engineer had to dive in there and do that Back to the Future kind of grab two cables and sparks going through their chest and yank these things apart because they were talking in weird languages and doing strange stuff. And it had to be separated before they took over the world, you know, Skynet version 2.0. But what happened, the reality of it, was actually quite different. Two systems were giving the ability, oh, come now. Maybe I gotta hit this thing harder, but yeah, this thing doesn't like me talking about it. It knows. So anyways, what actually happened was a couple of systems were giving the ability of English language construct and an inference engine to be able to negotiate. And these two systems were given an impossible problem. There's 2 books worth nothing, there's a hat worth 7, and 3 balls worth a point each. And they were told to divide those resources amongst them. And they started off friendly enough, but pretty soon they're both just yelling they want the hat. AIs in a game type environment, which is representative of this model, get very aggressive very fast because they figure out the rules and how to succeed very quickly. And so they were just screaming about wanting the hat, and it just got to be a pointless exercise. It's not like they were sub-communications channels out into the, bouncing off the moon and back and whatever else. It was just simply that they were both wanting the same thing. Now, for today's talk, we're going to put this in the perspective of antivirus, and we'll kind of keep it there. There's been 2 ways that we've dealt with, man, I hate having to check every time, see if that thing popped up. I'm sorry, I'm spinning. But anyways, there's been 2 methods that we've dealt with AV historically. The first one is that we would get this file in. It ends up being malicious. So we'd use MD5 or SHA, and we'd create a hash of that file. And we'd stick it over on a pile. Another piece of malware, we'd go out, get another hash, throw it over here. Email comes into the system, the AV side kicks off, and it gets the file off of the email, runs the hash, and if that hash matched anything in that pile, we knew it was malware. There were a couple of problems with that. The first one was the pile gets to be unmanageable after a while. Very, very large. Difficult to chew through it. The other one was that it wasn't reactive in nature. If anybody's played around with hashing functions, if you take an 8 gig file and in the middle of it, you flip a 1 to a 0, the hash value that comes out is nowhere close to related to the other one, to the one you started with. They're completely different. The mathematical operations that are involved in hashing take it out to where it's not even recognizable. And so cyber criminals would put a comment line in a piece of malware, and it would throw the hash off, and it would successfully go through. So we came up with something different. And at Fortinet, we came up with content pattern recognition language, but it's used by a few vendors out there. And here's the concept. You take a file, and you unpack, unwrap, unencrypt it as far as you can to the point of detonation, and you look at these indicators of compromise. Then you run it through a sandbox, and you look at indicators of compromise. And what that amounts to are little code jumps. Encrypt all, connect out to a C2 server, start PowerShell, whatever it may be. You've got behavior associated with a pile of ones and zeros. If you take an emulator mode and stick this software in there, the malware, you can see the jumps. And what we're interested in is pulling out those jumps, unencrypted and encrypted. You can do both. And we pull those jumps out, and now we have a code block. And we can put a bunch of code blocks together and create a super signature, if you will, so that if somebody changes, who cares? We've still got code blocks that relate back to that malware. Not only that, but brand new malware comes out. Something not seen. Here's a new name malware, and we still catch it. And why is that? Because criminals reuse code. Getting that 0-day vulnerability is everything. But that delivery package has to be reused for the most part because it takes so long to create a true 0-day delivery package to put that, to exploit that system vulnerability, that application vulnerability. And so they reuse code a lot. They have to. They got to get to the market as quick as we're trying to patch things, right? And the information gets shared at the speed of light out on the dark web when something's discovered. So again, they're not lazy. They're just forced to reuse quite a bit. And it's that reuse is where we get them with this, because we'll see these code blocks pop up. And if the AV doesn't get them, we have IPS in the background, or we have DNS that we're looking for reputationally, IP addresses, et cetera. But on the AV side, we catch them with the reuse of these code blocks. Now, back to AI real quick. Keep that AV in mind. It'll come in handy here in a little bit. But let's go back to where this stuff all came from. And it was actually Alan Turing, the brilliant mind of Bletchley Park, that came up with the concept of AI. And this is way, way back in the early 1930s. He said a child's mind is kind of like an empty computer waiting to be filled with knowledge and experience to be taught. The brilliancy of what he envisioned was right here in these 3 bullets. He knew that in order to have a machine that could think, you would have to take a seeded population of stuff, put it through there, and get something that was relational back out. He also knew that you'd have to have some kind of a variable weighting scheme that could change over time so a system could learn. There'd have to be variable pieces in there. And he also knew that there'd have to be a method for taking out the worst possible solution while retaining the best. The problem was he didn't have the gear of the day. The gear of the day couldn't really support this. Just couldn't build it. Great theory. So if we look at the timeline from him forward, he teamed up with Clean and Church in the later 30s, and they created a formal proposal of what AI would look like. And in 1943, a very basic model of it was built, and it was proven to work. Very, very basic, like the Hadron Collider over in Australia, or Austria, wherever, Switzerland, sorry. The first particle collider, has anybody ever seen that? Yeah, it fit right there in the palm of your hand. Very tiny little device. It was a toy, a physics toy, really. That's the same thing with this. They built a very basic one in 43, but it proved the theory was valid. A year before I was born in 1956, it became a formal discipline at Dartmouth College, and things chugged along pretty well. The governments, primarily British and US governments, invested heavily in AI. And then along comes Richard Nixon, and he decouples gold from the dollar, from the US dollar. The US dollar happens to be the world's reserve currency. It's what we base a lot of our currencies on, right? So he decouples gold from it. We go off the gold standard, and the next thing you know, economies start going into little sputtery spins and things because the lack of trust in currencies. You know, a fiat currency is no longer trusted, right? Now we're pretty much used to it, but back then it was a big problem. And so next thing you know, we had runaway inflation, deflation, currencies were just going crazy. In the US, when I was a kid, I remember this. They implemented pricing controls on bread, gasoline, and milk. So the funding that was being used for AI got pulled out and put into social programs. So the governments could kind of start keeping care of the populations. And AI kind of went into a dip, into a winter, if you will, to where it was ignored for a while. And then it started to pick back up. And we saw Lisp created at Bell Labs. It was one of the first languages of AI. And things were humming along. It was used in medical fields and things like that. And then something else occurred that was kind of interesting. Our televisions that were bubbles with phosphorus that ion guns shot things onto, all of a sudden this little character comes on and he's waving a cane looking like Charlie Chaplin, waddling around, and it's the advent of the IBM PC. Now, this amazing thing could sit on a desktop and give you like things like black and white pie charts, spreadsheets. It was amazing. So a lot of corporate investment turned away from AI because all their business problems could be solved with this desktop machine. And so it went into this second little dive of winter. After that, it started to pick up. And IBM actually came up with some of the earlier, larger, well-known implementations of artificial intelligence. When I was a kid, I used to watch Kasparov and crazy Bobby Fischer play chess. And Deep Blue beat Kasparov at chess. It was an amazing thing. It was a big headline. And like I say, just kind of kept rolling along, growing. 2015, just a scant 3 years ago, there were 2,700 AI projects in flight, up and operational and working alone there. And then last year, Elon Musk said that we would need to regulate AI before it hit the 100-year mark, which we're just about there. It's that old. But that's, that's putting worms back in the can. It's like saying we should go ahead and get rid of digital currencies or control all the drones in the US. Good luck, right? You can't put this stuff back. It's already out. Right now, you can go out and download AI applications, put them on your laptop tonight and start playing around with them. Or if you want, you connect into the cloud. Do it. Just go out and interface with an AI, give it a problem, teach it, do something with it. You can play with this stuff. Right after he said that, Vladimir Putin came out and said, whoever controls AI is going to control the world. And that's kind of the state we're in right now. Should we regulate it? Can we control it? Who has the biggest, the best, et cetera? So let's get into how this stuff kind of works and how we modeled it. And basically, it's kind of created in our image to some degree, and how we solve problems as human beings. The first approach we use, and the one that we're most familiar with, is the supervised learning approach. It's reinforcement, basically. When we went to school, we're in kindergarten and we get taught the sky is blue. Okay, the sky is blue. We take a test. What color is the sky? It's blue. Ding, there's your gold star. Walk on. What color is it? It's red. Bap, go back, try to learn again. It's this reinforced learning type of thing where we teach, we test, and based off of the results, we determine if you move on or if you get reset to some degree. And then we have this unsupervised learning stuff that we use as human beings to figure out our environment and what we should do with this information that's coming in on a flood second by second. The first unsupervised approach is clustering. We group according to similarities, or when I walk into a room or an event, I'll see people clustered together standing, and you'll see different things, and you start to make inferences about what you're seeing, or reactions among a couple of people. You start to cluster them based off of if two of you look at each other and go, this guy's full of crap, or whatever, I'll cluster you together. I'll start lumping and grouping, according to what I see within my environment. The second method we use is dimensionality reduction. If X and Y, then we have Z going on. Sorry for the same joke for the dudes, but here it goes. Dimensionality reduction. If it's my wife's birthday and I forgot it, I'm probably sleeping in the car in the driveway. There may be a variable of whose driveway I get to sleep in, depending on how angry she is, but it's this dimensionality, X plus Y, and we get this result. This is our dimensionality reduction approach. We use it walking around every day. Another one is structured prediction. We all wish we could be the weather person and get paid to be wrong, like 30 to 60% of the time, but we're all kind of weathermen when it comes down to it. How many people drove here today? You don't have to participate if you don't want to, I'm sorry. When I was driving here, I was looking at where I was thinking about where I'd have to turn, what I'm doing, looking at the GPS, looking at my speed, but I'm also looking at the traffic around me, the holes, the slots, brake lights ahead. Are people jammed up behind me because I'm going too slow? When do I have to start shifting over so I can get into the off-ramp? Things like that. And I use this structured prediction not only to take care of where I've got to go, but also to learn about my environment and how to react to it. And then the last one we use is the anomaly detection. It's the where's Waldo moment. What's here that should not be, or what's missing that should be here. And that teaches us about our environment. Now, when we start talking about deep learning, machine learning, AI type systems, they can use these different methods of learning. But for a deep learning system, this is actually the best one, this supervised learning approach. And we'll go through how that works graphically. How am I doing on time? Good. So, one approach is to use an artificial neural network or the multi-layer perceptron. And how this thing works is it consists of layers, and you have hidden and open layers. The open layers, you can see what's going on. You input here, you can see that you input something, and it went through and it popped out over here. Okay, 2 open ones. Now you have hidden layers in there as well. And a layer has got a general responsibility within the system. Input is for putting in files, output is for getting the output, and then you'll have other layers that have other jobs. They're called hidden layers because we're not really sure what's going on in an atomic structure. What's going on at that little bit level. The operations are so fast and so furious, you really don't know at any given time unless you stop the whole thing, freeze it, and try to go through the step. And when you're talking about large systems and the velocity at which they're operating, it's about impossible to do. Now, each one of these layers, like I said, have a general responsibility. The system that we built, we had 2 layers, 2 hidden layers. One was to look for malware or recognize it. The second layer was to look for clean, and we set them against each other in juxtaposition. They fight to determine if something's okay or not. And we'll get into how that works in a minute as well. So these layers have got general responsibilities within the system. A job function. Now they consist of nodes, and here's the second term you're going to want to walk out with so you have some knowledge of AI and you can talk about it. Layers, nodes, and features. Nodes are small applications, tiny little black box applications. And what they do is they get fed something off of a stack, a piece of data, and they look for it. Now, the amount of what they're looking for that gets seen is a percentage output of their valuation. So there's your first clue into that weighted piece of AI, right? So I pick up something, I see 90% of it, I'll pass forward 90% through the system. So they've got a very, very basic, limited function within this system, but the important one is that they get something to look at, they search for it, and whatever amount they see, they'll pass forward. Now, the thing that they're looking for is called a feature. A feature is a point observable characteristic. Facial recognition features, right? But facial recognition, the features are measurements, interpupillary distance, the size of the nose to the shape of the head, facial hair or not, color of the eyes, color of the hair. All of these things are little things that features that this system's looking for. Within this, what we're doing is we're parsing apart those malware files and clean files actually, but we're tearing it apart into these code blocks, and we're using that as the basis for this. Now, this pile of ones and zeros, the thing that the node looks for, it's a one-to-one relationship with a node. And what that means is, as a node in a cycle of looking for something, I'll go out and I'll grab that pile of ones and zeros and I'll look for it. No other node's going to look at this. When I'm done, I don't go out and I don't grab another one and look for it. In a cycle, it's a one-time shot as it goes through the system. And that's important. You'll see why in a bit. These are maintained in this huge feature repository, a big stack of them. Now, the quality of what we have is the critical part of it. We have the node that's going to do its percentage of how much I found, right? But the feature is weighted before it comes in for the analysis. And this is the second little piece of Turing's brilliancy in a system having to have these weighted variables, is this feature comes in with a numeric value. And that numeric value can change over time of that feature, of that code block that comes up. And so that's the real variable that can be applied by the larger system. The node is relatively dumb. It looks for a percentage and passes it forward. That feature can percolate up and down in the stack over time in relation to those other features. And we'll show you how that works. It's these three capabilities: a layer that has a general responsibility that consists of nodes that are doing that very simple little operation, picking up features that provides a system with the ability to learn. We start out and we'll feed it the initial data sets and let it start plucking out code blocks and things like that. And it's extracted and put over into this repository. And I have a graphical model we'll see of that. Don't get too wrapped up right now. The main thing is that this system, as it's pulling these features out, it starts seeing them repetitively. Now, if something indicates malware and you see it a couple times, that's going to bump up its importance in that big stack of features. And so when we're sitting there cooking these features out that are really important, it's kind of like processing gold. A gold mining operation, you'll see a large dump truck come along, and they'll take that ore and put it through all kind of centrifuge, water, chemical, heat, all this processing, get this little piece of gold. And that's kind of what we're doing with that pile of features, those code blocks out there, is we're trying to find the ones that are significant. And the system can actually change that weighting of that pile, the individuals within it, to produce this kind of gold. The more it sees a feature, the more important it is, but more importantly, the surety of the tell, the poker tell. You know, like somebody grabbing the ear when they got kings. This feature, every time I see it, it indicates that it's a clean file. That's important. I'm going to pop up the numeric value of that one in the stack so that over time, that mountain is of information, those code blocks, actually becomes a pyramid with the most important features having percolated up to the top of it. Now let's talk about what happens on that atomic structure with a layer and a node and a feature. If we could stop this thing and take a little photograph in time of feeding in a file and a node doing its job, this is what it would look like. We fire this thing in, we break it down into the binary. A node goes out and grabs a feature that's worth 100 points, okay, out of the stack. That's its job, is to get this one. And it pulls it in. Here's a 100-point value, but it only sees 90% of the congruent ones and zeros in that block. And so it passes forward a plus 90. Now, the next layer, it connects to the next node and the next layer, and this one's looking for clean indicators. And it goes out and it pulls a code block, and it does the analysis, and let's say this one's worth 100 points as well. It pulls up that 100-point code block, but it only sees 20% of those ones and zeros congruent within that entire file. And so it's a 20% valuation, and it really is just a simple add and subtract. The result is a 70% probability that it's this and not that. Easy stuff, right? Dumb math when it comes down to it. The complexity comes in when you consider that a layer of an AI system has its nodes, right? Every node in that layer connects to every node as it goes through that system. The one that we happen to build has 2.3 billion nodes in the malicious layer and 3.2 billion nodes in the clean layer when we do this analysis. And we have that output decision that pops out at the end of it. Now, individually, that node-to-node operation is relatively simple. But here we're talking about 2.3 billion times 3.2 billion operations that occur every time we fire a file into it. And that's where the complexity comes into play. You have to have massive parallel processing on these things to be able to accomplish this. Initially, when we fired it up, we could do 58 samples per second, which is roughly 5 million samples a day. Now, you remember that pile of gold that we're mining, and we're getting those features that are more important and they're percolating up to the top? As we find more and more of those, the system gets kind of like smarter and smarter, right? Because these things are coming up and it's using those top ones to spot the stuff because they're the hottest and of what's happening. And it actually gets faster over time because overall within that system, it comes up to a surety of whether something's malicious or clean quicker as those features get clearer and clearer and percolate up to the top. So it actually gets faster than this as it goes along. But there's the real complexity, is the number of operations that are occurring per cycle within the system. Everybody with me? All right, take a deep breath. And we'll continue with the next part. How do you even build one of these things? Well, you have to start off in a training type environment. And you kind of have to let the AI create that big pile of ones and zero code blocks. If you try to have humans do it and rank and rate them as best as they could, it would be the equivalent of sticking 20 monkeys on typewriters, hitting the clock, the stopwatch, and waiting for Shakespeare to pop out. It'd take forever. So we have to let the system actually do it for us. And what we do is we feed it training files. They got these little markers saying, hey, this is a clean file, this is a malicious file. And the system had ingested, okay, this is malicious, and it breaks down those files into code blocks. Hey, these are malicious indicators. You know, those little jumps, those ones and zeros. All right, this is malicious. Gotcha, 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 gotcha. And you feed in more and more files. And as you feed in more files, it starts to see repetitions of those code blocks. And as it starts to see the repetitions, well, it's going to start popping up the importance in that stack. This is always a clean. This one's always malicious. Da, 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 and it starts mining that gold for us. The system kind of has to teach itself when it comes down to it. We help it by telling it what it was fed. How do we know if it learned correctly? We give it the test. So it's got the features that are built down in the repository. And now we're going to feed files in, but we're going to remove the marker. We're not going to tell it what it's being fed. And again, it ingests these things and chews them up in code blocks and starts looking around. And even as we're training this thing, it might add new code blocks and continue to learn. The only thing I ever learn when I take a test is I should have studied longer. This thing continues to learn as we're testing it. Now, it comes up with what it thinks is the correct answer. Is this thing malicious or clean? And it puts it over here. Now, we know what we fed it, so if we take what we fed it and compare the output, we'll know if it learned correctly. If it learned correctly, $200, pass, go, be happy. If it didn't, we swat it and stick it back to a known state. We'll kind of erase whatever we just did, take it back, and we'll try to feed the files in a different order, or maybe take a new training set of files and try that approach to see if we can get it to continue through this cycle of training. This 5.5 billion node system took 5.5 years to train. One of my main points about this is not trivial stuff. When somebody comes along, hey, we built an AI last year, boing, there you go, you know. That's not how this works. IBM found that out the hard way, and they're the masters of this. You know, Watson and Deep Blue, right? A few months back, there was an article I read where they tried to train Watson, a version of Watson, to recognize cancers. The type of cancer, the stage, and the progression diagnostics, and then come up with treatment advisement. And they shortcutted the training cycle on it. They tried to compress and do some heuristics on data compression sets and stuff like that to get it up and spun because they had customers that were wanting it. Now they hurried up, right? And at the big test, it blew up. Couldn't recognize cancer. It couldn't give a good diagnosis. Couldn't give good treatment options. It was bad because they'd rushed this stuff along. Training this stuff is not trivial. You step into wanting to build a real system that's going to really do something for you, it takes time. It takes a lot of work. But anyway, so that's how we kind of train and test it. So the result should be that we have a system that we can fire these files into, and this is getting broken down into the code blocks, and the little nodes out there in those layers are spotting malware and clean files. And while we're feeding this stuff in, it's continuing to learn. It's constantly feeding new features into this, and it's popping the weight value of the features that exist based off of what it's ingesting and seeing. So this is the model, and then we have our output of malicious and clean. This is the result of an AI system. This is what we're after. Now, do we want a whole bunch of features? Is it a good thing to have lots and lots of features? No. Not really. What we're really after is quality over time. We want that goal to percolate up. Right now with this 5.5 billion node system, we've got around 9 or 10 billion code blocks laying in the repository that they use. And when this cycle is initiated, it goes out and it grabs the top 5.5 billion of those features and does the analysis on them. And of course the result is, yay, we get to separate out malware from clean files very, very easily and very, very well. Now, I've got about 10 minutes left. How do we bring in new malware samples with something like this? It's not a trivial problem. These new features are naturally regressed in weight. They have a value of being seen one time. So we have to do some kind of a false weighting to a feature if it's important. And we've got to figure out if it's important or not. But we don't want to do it in such a way that it subverts that stack. We've taken years to build that stack. We don't want to go in there and just start kicking it around and messing it up. We can't use single samples. It would heavily skew the results of what we're trying to perform here, which is figure out how important these things are and introduce these large errors again if we just took single samples. And one of our approaches at Fortinet, not trying to sell you guys anything, just think. We wanted to be able to do this in such a way that we could integrate it in production with our customers seamlessly and quietly. Just do this. And we had our reasons. One of the things I didn't bring up on that CPRL, you know, that Uber signature, is we had to have our engineers tearing apart malware by hand, taking out the stuff that they thought was important, going over, seeing if we already had stuff created for it, other signatures. And then the ones we did, they'd have to remove out, and then they'd have to build signatures, and then they'd have to QA them, and then we have to get them out to our customers. And that was painful. We wanted to build something that would support the customers seamlessly and also alleviate engineer work, give them a break, let them go do more interesting things. So here's what we came up with. We basically have about 130 threat feeds. You guys are probably familiar. Guys, when I say guys, I mean girls too. Don't start, throwing things at me. But we have about 130 feeds that we use, sticks and things like that everybody knows about. Out there, you can get new samples and things, CVEs. But we also have about 4 million of our devices around the planet that's constantly collecting stuff. And we also created something called the Cyber Threat Alliance, which is counterintuitive and a very fun experiment in sociology. We went to our competitors, and we're talking Cylance, Carbon, Palo Alto, Cisco, and we said, hey, why don't we get together and join up and share threat intelligence? And it's just better for our customers. And reluctantly, we got this pile now of 20, 30 participants, and every week, each participant is required to submit something to the group. The survivor version of this is that every week the group judges what you input. And if it's deemed to be insufficient, you're chastised and scolded. And eventually you can be voted off the island. It's kind of fun and kind of weird, but we're actually getting some good intel. And they'll share all kinds of different intel, not just AV stuff. But anyway, so we've got this incredible chunk of stuff that could potentially play, that we have access to. So let's go ahead and feed it into the system. and we're going to mark it. We're going to stick the pin in. Now we have a smaller AI system sitting there, and we're going to do a training event. We're putting a pin in here saying this is malware. Roger, this is malware. And it chews the stuff and starts creating features just like it did back in the original testing phase. Now we have a second system as well. This one does the undetonated. We unpack, we unwrap, we unzip. There's only so many ways you can do that, down to the point of detonation. We hooked up another AI to a sandbox and did the same thing there, except now we have detonated samples going through it. And we use that to feed IPS and some other things. We'll get to that in a minute. So anyways, we have these disparate feature sets. These may or may not be over here. These may or may not be over here, but they're kind of like non-matching sets. Now, to get away from the single sample, we use a rolling input. We go back like 3-6 months, and we'll take everything we get that's new, and we'll feed it through these two systems. So every day we're incrementing forward. We're not taking that single sample. We have an algorithm that we use for that 6-month window in relation to how long this system's been in existence and so that it knows how to weight this stuff properly. The AI side is really, really quick because it doesn't have to do the detonation, sandbox, anti-sandbox maneuvering, and all the other junk. It'll do millions a day. The other one, can do about 10,000 samples a day, 20,000 samples, which is sufficient for keeping up with new stuff. The features are created just like in original training. Now, the code blocks and behavior that we've torn apart using this system can be used to serve the purpose of feeding several of our security products. Think of the Native Americans and how they treated a buffalo. By the time they killed it and dragged it into camp and got done tearing it apart and using it, there was very, very little left over. And we do the same thing here. We're trying to get every bit of intel we can out of everything we get. So let's talk about just this undetonated side and what we do there. So we've got these new features. Remember, we did the training event with it. Here we are. We have what this thing thinks is brand new stuff. Maybe it is and maybe it isn't. Let's do a comparison on the production feature set and subtract off what we already had. Now, when we do this, by the way, what happens to the features in here? They get popped up a little bit in their weight value because we saw this stuff again, and that's important. So we have an algorithm that kind of chunks those up a little bit, and here's the new features. Now, we take the ones that were seen a couple of times or that have some criticality of dimension to them and keep those and subtract off the ones that aren't very interesting to us from the system perspective. We're going to clean out this AI now and put the resulting features into the system. Now we're going to run the malware samples through, and we're going to pull the pin so it doesn't know. It's all malware, but we're going to remove it and see what happens. So it chews through and it comes up with the features that were really, really important, critical, good. The ones that caught those malware samples are tagged. All right? Now off of those, what we'll do is we'll hang a little weighting value and stick them into that production feature set according to the time and the importance and how well they performed. They get inserted into the stack by the AI system. Now over here, we have a little CPRL. Remember the super signature? We have a little engine that takes every possible permutation of these code blocks, creates those Uber signatures, and runs the malware through it. And we look for the ones that perform the fastest and most accurate. And they're pushed out to our customers automatically. Now, what about the sandbox side? What are we doing over there with the detonations? Basically, we're going down here into the production feature set, and we've got those features, and we're going to subtract those out again and take down the most important ones. We're going to empty it out, put it in, feed it through, and we get something down here that's relationally important to us. Once again, we're going to kind of follow the same procedure, but these are detonated. Why do we want the detonated stuff? Because we can use that for URL reputation, IP addresses, IPS signatures. There's lots of stuff that we can glean out of there that's not necessarily AV. A lot of the detonated stuff, once the malware detonates, we can see the C2 server URL, IP address. that the malware is trying to connect out to in order to download the system information and get uploaded orders on how to execute against the vulnerability. So we get a chunk out of that. We break these things apart and use just about everything we can get to. So the result is we've got kind of like this dual protection thing going on. Just on the AV side, there are 4 artificial intelligence engines. By the way, the engineers that used to make those signatures, doing the grunt work of it, we have them doing more interesting things that humans should be doing instead of this. They're out looking at botnet takedowns. We're up to, I think, 600 zero-day vulnerabilities we've discovered in software and hardware. They're out there doing zero-day analysis on products and things like that. They're doing the things that take some human intelligence to do. This is just the grunt work side. So we let it take care of it. Now there is, I said there were 4 systems. You saw 3 of them. There's another AI. Every once in a while, the engineer will grab one of these signatures and QA it to make sure that the system's functioning correctly. And we have another AI that's watching that QA process and learning how to do it based off of the human activity. So there are 4 systems, but the result, we're trying to significantly increase the cost of doing business for the cyber criminals when it comes down to malware. We have unsurpassed accuracy, proven, validated, extremely adaptive, dual protection, blah, da, 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 da. It works. It's put us up into the right quadrant in a couple of different areas of independent lab tests. This stuff really does work. So I've only got another minute or so. Let's get the takeaways done, and then you guys can or I can take a break and you can get away. So AI is not trivial. We've been at it for 8 years, 5.5 years just to train this system. And it's not like we were doing it, on spare time, weekend time. This was a full team implementing this thing. Production for almost 2 years. It significantly increased our catch rates and our reduced our false positives down. The accuracy of it really is pretty incredible. It should ease technical resource demands. If you're going to bring an AI solution into the shop and you hear, well, you just got to do this for it and this for it and this for it, be leery. Typically, technical resources are stretched thin enough as it is. You shouldn't be investing a lot of your people's time to support an AI that you bring in to solve a business problem. That's just not what they're made for. You should not have to watch it and tell it right from wrong. There's some of them out there that it's not, no, this one's okay. Okay, I got it, it's okay. And every once in a while you got to step in because somebody's raising Cain about it. Beware of buzzwords. AI is a big one right now. Analytics systems are being touted as AI. And last, if anybody comes to you and pitches AI and they don't have some fundamental knowledge of how it works or what it's really doing, they're probably just buzzword selling to you. Just be careful out there. You've got some basic terms, you got some concepts, you're armed with knowledge. Anyways, thank you so much for your time today, everybody. I really do appreciate it.